So hi everyone, thank you for being here. Today we have Paul Dobson from TU Delft who will tell us about subgeometric hypercoercivity for piecewise-deterministic Markov chain Monte Carlo methods. Paul, please go ahead.
Thank you. Thank you very much for inviting me to talk and for turning up to listen. Today's talk I'm going to be talking about the theory of hypocoercivity for PDMPs, in particular in a subgeometric setting. And this is based on a project I did with Christoph and Andy Wang from the University of Bristol. The structure of the talk is going to be, to start with, just going to give a broad introduction to the theory of hypocoercivity on a fairly abstract level, then move on to discussing the particular processes that are of interest for this talk, which is PDMP, and discuss how the abstract theory of hypocoercivity applies to these processes, and what we lose when we remove this geometric situation, and what we need to deal with the weaker subgeometric setting turns out to be the weak Poincaré inequality. And then finally conclude by drawing these ideas together to give the result for the subgeometric setting. So first of all, what's the general goal? So the question is, if we're given a stochastic process, Zt, and we want to ask, how fast does this converge to equilibrium? So we're going to do this by talking about its semigroup. So I'm just going to denote its semigroup by Pt, and this is just the expectation of functions of the process given the initial condition Z. We want to determine how fast this converges to equilibrium. We're going to describe the equilibrium by assuming there is an invariant measure, and we're going to assume it's unique. And this measure is going to be denoted by pi. And throughout this talk, pi is going to have a smooth positive density, which is given by e to the minus u. And then script z is just a normalization constant. So in a more MCMC context, we could ask if we want to draw samples from some given measure pi, and suppose we've been given a continuous process that targets this measure, how can we determine how fast this process converges? Well, first of all, what do you mean by convergence in this context? So for this talk, we're always going to be talking about L2 convergence, where L2 is weighted with respect to our target measure. So a first guess of what we might want to try and prove is we try and prove that the semigroup converges to our measure pi in L2 at an exponential rate. So we could prove this sort of result if we were in some sort of coercivity regime. And I want to point out that as t tends to 0, this estimate is sharp. Now it turns out that this is too much to ask for our setting, so we're going to need to weaken this slightly. So the first thing we can do is, instead of asking that this inequality occurs with constant 1 here, so where the left-hand side and the right-hand side match at time 0, constant in here. Now, one advantage of introducing this constant is that requiring this inequality to be satisfied is now stable under changing the norm that we're using to an equivalent norm. So if we transform our L2 norm into some equivalent norm, where we hope that convergence is easier to prove, we can then return to L2 results just by converting the norm back. And in fact, this is going to play an important role in the way that we'll prove stuff. And this would be what we would be aiming to prove using hypercoercivity in a geometric setting. So by geometric setting, I'm always meaning exponential decay. For this talk, I want to talk about subgeometric convergence, so convergence that's slower than exponential. So now the question is, we find some rate psi and prove that our process converges with that rate, where we no longer know what this rate is a priori. So this is the goal. Now the question is, what's our strategy? Well, I want to first try and explain this strategy with a fairly simple example. The example I'm going to use is just a particular ODE. So this is just a nice, simple linear ODE. And one can check quite quickly, either by looking at eigenvalues or just by solving this system directly, that this process has one equilibrium at 0 and, roughly speaking, converges exponentially. And in fact, if we just plot the radius of this process, and I've compared it, so the radius is in red, and in blue and green I've just produced two exponential curves to compare. We can see that most of the time the process seems to be going down exponentially. But if we were to try and prove that this decays exponentially, one fairly straightforward strategy would just be to take the time derivative of the norm of this process. But what happens if we do that? Well, we can just calculate what we get, and what we get is minus the velocity process squared. So this is non-increasing, and whenever the velocity is non-zero, this decreases. And as I said, if we look in the picture, this often is decreasing. But there are certain points, namely when the velocity is 0, when this is 0. For example, 0.10, which is the point that we plotted here. So what's happening graphically is that the path of the process is at some points moving tangentially with respect to the unit circle, which is the set of points where the norm is 1. But most of the time, this process is well behaved. So to combat this, or as our strategy to deal with this, what we're going to do is try and find a different norm where we don't have this problematic behavior where the process is tangential to the norm. So the game is going to be, how can we find some equivalent norm, but where we can prove convergence? Now this was just for a fairly simple example. And I say for this particular example, you can even solve the ODE and say whatever you want. But we want to know, how can we do this in a more general context? So our strategy is based on this abstract coercivity strategy introduced by Dobson, and Schmeiser. And what we do is we take our semigroup, PT, and we're going to let L denote the generator corresponding to the semigroup. We decompose L into two parts, a symmetric part and an anti-symmetric part. And then let's just try the same strategy that we used on the previous slide. We take the norm of the semigroup squared and we differentiate it. Well, if we differentiate the semigroup, we get the generator. Now, the anti-symmetric part of the generator in this expression will just cancel. So we get left with the symmetric part. Now, if we want to try and prove convergence, what we need is to obtain some sort of term on the right-hand side that we can control. So the first condition that we may ask for is that if S is coercive, which means that the inner product between SF and F is less than or equal to minus lambda norm of F squared. If we had this inequality and we apply it to the line above, we have that the time derivative of the norm squared is less than or equal to minus lambda norm squared. So we can just straight away apply a Gromov inequality and obtain exponential convergence. However, in the settings that we're going to be working, this operator S is not coercive, so we need to weaken this condition. And the condition that we'll be using is that this coercivity estimate is only satisfied with the right-hand side restricted to some submanifold, some subset. So we just have this projection, 1 minus pi. For the ODE example we just considered, we saw that the right-hand side that we got was minus the velocity squared. So the projection in that case, or 1 minus the projection, was just projection onto the velocity space. So we can see here that this is good in some directions, namely the directions given by 1 minus pi. But we have no control over the remaining directions, the directions given by pi, if you like. Or in the ODE example, this was the positions in x, the velocity of the position. So now our strategy is to find a new norm, which when we attempt this strategy, we get some new terms which we can control. So let's have a candidate new norm, or new norm squared, right, which we're going to just call h. And this is going to be given by, in the first part, just the original norm squared. And then we're just going to introduce this new operator a, which for the moment is just some bounded linear operator, which we'll choose later. And then we choose this var epsilon to ensure that this function, or the square root of this function, is equivalent to the L2 norm. Then what we need to do is to find some conditions whereby we can use this Grunwald type argument. So when the time derivative of this new norm applied to the semigroup is less than equal to minus lambda times the new norm. Well, let's just look at what this gives us. The left-hand side we can just calculate just by using, again, that the time derivative of the semigroup gives us the generator. The generator we've split into two parts, the symmetric part and the anti-symmetric part. And then we can decompose this slightly further by using this projection pi. Now for a particular choice of A, which is namely this one, which is 1 plus t pi star t pi inverse applied to minus t pi star, we can rewrite the second term so that it has somewhat of a similar structure to our coercivity condition. Namely, we've got this function phi of t pi star t pi applied to f, then interproducted with f. So now we have two terms that are of the form operator applied to function, then inner product with function. So if we could understand the sort of, using the word coercivity here, the coercivity of S and the coercivity of t pi star t pi, then we can hope that these two terms will give us all the directions that we require. And then we just need to bound off the remainder terms. And this will be our strategy. The next question is, well, what are these operators? We've seen that S is the symmetric part of our generator. But what's this object t pi star t pi? So for this, we need to understand what we're applying it to. So let's move on to discussing what are PDMP and what are the processes we're going to be considering. Well, PDMP, piecewise deterministic Markov processes. So first of all, from now on, we're going to split our processes into a position and a velocity component, or denoted by the position x and the velocity v. Now, as the name suggests, these processes are deterministic for most of their life. Processes are made up of three things. First of all, deterministic motion. And just to keep things not too abstract, the deterministic motion we're going to be using is just linear and with constant velocity. So the position updates according to the velocity, and the velocity remains constant. So on the plot, these are just the straight lines. But then we have event times. So these are times at which some events may occur, and these are given randomly according to some rate, lambda. And lambda here is allowed to depend on the position and the velocity. So it's allowed to depend on the process itself. And whenever these event times go off, an event can occur. And I'm going to be fairly vague here and say that we can have two types of events. We can have reflections, which are the events that occur in this image, or we can have refreshments, where we just draw a new velocity. Now, because we've split this process into a position and a velocity, I'm just going to change the notation we're using for the invariant measure. So where previously we were talking about always targeting this measure pi, we're now going to say the invariant measure is some measure mu, which is the product of the measure that we're interested in, pi, which is given by e to the minus u, and some fixed measure for the velocity, which typically is something fairly simple, like a standard Gaussian measure. So we can write down the generator for these processes. So again, this is made up of three things: the deterministic part, which is occurring with constant velocity, a set of reflections, so being, again, somewhat vague about the reflections, but we've got some operator bk, which describes them, and this has fairly nice properties, such as bounded, linear, when it squares you get the identity. And then we have refreshments. And refreshments we're just going to assume take place by resampling from the measure, the invariant measure for velocity, and occur at a constant rate, lambda r. One could allow slightly more broad assumptions here, but I want to try and keep it fairly simple for this talk. And then we choose this rate lambda k to ensure that we have the correct invariant measure. So an example of such a PDMP is the zigzag sampler. So in this notation, we would take the number of reflections to be the dimension in which we're working, and each operator bk works by just flipping the sign of the kth coordinate of the velocity. And then if we choose lambda k to have this form, so it's just a positive part of the product between the kth component of the velocity and the kth derivative of the log density u, then we have the correct invariant measure. And here is a brief plot of what this might look like. Again, so it's moving with piecewise linear components, and then it has random events where the sign just flips. Another example, which I'm actually going to concentrate on for the rest of the talk, is the bouncy particle sampler. So again, we have the same form, where it's deterministic, reflections, and refreshments. The deterministic motion and the refreshments are given by the same as the zigzag sampler, but reflections now occur according to this operator. So the velocity is now reflecting off the contours of our potential function u. And fix ideas slightly further, we're going to take nu to be a standard Gaussian measure. And then pi is just integration with respect to this measure nu. So from now on, I'm just going to talk about the bouncy particle sampler. This is purely to stop having to introduce more notation. But the ideas that I'm going to talk about for the most part will extend to the more general PDMP that we introduced before. So these are the processes that we're going to be talking about. Now I want to return to the question of how does the hypocoercivity structure work in the setting of PDMP? So what are these operators that we were talking about? So this was considered in a paper by Andrea Dermus and Russell in 2018 and works along the same framework as been introduced so far. So we take the generator as we introduced previously, and as in the abstract setting, we're going to decompose this into two parts. The symmetric part and the antisymmetric parts. The refreshments are already symmetric, so they go into the symmetric operator. The deterministic parts goes into the antisymmetric operator. But we're going to have to split the reflections further. So we do this by, in a way, splitting the rate into two parts, lambda E and lambda rho. Lambda E is just given by the absolute value of the inner product between V and grad U. So if we remember that the switching rate was the positive part of this inner product, lambda E is the absolute value of the inner product, and lambda rho is the inner product itself. So this is the operator S and the operator T. Remember that we had this splitting of this. We differentiated the new norm, and then we split it into these different terms. And we highlighted the first two terms. We said that if we can control these, if we understand these two terms, we can hope that this will give us control of all the directions that we need. So these two terms were the microscopic coercivity and the macroscopic coercivity. So first of all, the microscopic. So this is the coercivity coming from S. Well, in this, for PDMP, this estimate actually comes quite immediately because it just comes from the refreshment part of the operator. And we see here that what this is really is coercivity if we only consider the velocity part of the component. So S, in particular refreshment part, only really operates on the velocity because it contains refreshments, which is all about the velocity, and reflections, which only occur to the velocity. And if we took a function that doesn't depend on x, so if f is just a function of v, then this really would be coercivity. So what's missing here is the x direction, which is where the second term comes in. The second term is t pi star t pi, and it's basically a direct calculation to see what this is. And it actually has quite a relatively simple form, which is the acts on functions f by giving the Laplacian minus the inner product of grad u with grad f. So this is the reversible Langevin operator. In particular, because everything here has a pi in it, this actually only acts on the x variable. So this is a differential operator in the x variable, and it's reversible with respect to pi. So it's now got a new operator that's somewhat easier to understand than the operator which we started with. And in order to have the coercivity that we need, the macroscopic coercivity, this follows provided we have a Poincaré inequality. So we have an inequality between AG and the norm of g squared, where here g is just a function of x. So it's not a function of the velocity. Or in other words, if we have a gap in the spectrum of this operator A. However, the subgeometric case is precisely the case where this assumption fails. And this case was considered for degenerate SDEs by Griffiths and Wang in 2019. And we're considering it for PDMP. So we don't have the Poincaré inequality, but we need to still control this macroscopic coercivity term. And the tool that we're going to use to do this is the weak Poincaré inequality. So we said that A satisfies the Poincaré inequality if we can control the norm with the inner product between AG and G. A satisfies the weak Poincaré inequality if we can control the norm with the the same term, AGG, plus an additional term. And for the context of STs, and for the context that we need it, this additional term takes this form, where here this is the oscillation of G. So it's the supremum of G minus the infimum of G. And we have this new parameter R, which we can choose. So an immediate observation for this is that we now have to restrict our attention from just G and L2, okay, so with sufficient smoothness. So now we're also going to need to assume that these functions G are bounded. And this is going to be an assumption that we'll have to maintain throughout the entire proof. Now, unlike the Poincaré inequality, which requires reasonably strict conditions on the growth of your potential function u, or the decay of the target measure pi, the weak Poincaré inequality is satisfied under much weaker assumptions. And this is discussed in a paper by Rockner and Wang. But in particular, if for u sufficiently smooth, gradually I think merely needs to be sort of locally bounded for this for the weak Poincaré inequality to be satisfied. So really this is satisfied in very weak assumptions. However, the price for this is that it can be very difficult to find alpha of R precisely. And while you may argue that the Poincaré inequality is also very difficult to work out what this constant is, what we need to know for alpha of R is what its behavior is like as R tends to 0. I'll just comment here that if alpha of R were bounded, then we would be allowed to send R to 0. And if we send R to 0, the final term vanishes and we recover the Poincaré inequality. So the situation that's of interest is the one where the Poincaré inequality fails, but the weak Poincaré inequality holds, and this is when alpha of R tends to infinity as R tends to 0. Now, just to give an idea as to why this is so widely true, or why the conditions for this are so weak, it's because the weak Poincaré inequality just follows from a local version, a local Poincaré inequality. In particular, if for any epsilon small, any epsilon positive, I'm thinking of it as small, there exists some set, so think of this as a large ball in your space, such that this ball has nearly full measure, so it has measure at least 1 minus epsilon. Then there exists a constant c, such that this version of the weak Poincaré inequality holds. Then this version of the local Poincaré inequality holds. Then we can prove the weak Poincaré inequality from this one simply by bounding the final term in terms of the oscillation of G, and then letting this set get arbitrarily large. So, some examples for where the weak Poincaré inequality holds, but the strong one does not. First of all, if we take the function u to be minus d plus p log of 1 plus mod x, so in this setting, pi has tails that are polynomially decaying, so they're decaying with rates 1 over x to the d plus p, so d is the dimension and p is some positive parameter. Then the weak Poincaré inequality holds with alpha of R asymptotically looking like r to the minus tau, where tau is given by this function. And in this small plot to the right, we can see roughly what tau looks like. As p gets very small, tau explodes, and as the dimension gets larger, tau gets larger. For the second example I want to consider, we take u of x to be minus sigma x to the delta, for some delta between 0 and 1. So in this case, pi looks like the exponential of u. And so pi has exponentially decaying tails, sub-exponentially decaying tails. If delta were to equal 1, we would have exponential tails. And in fact, for delta greater than or equal to 1, we recover the Poincaré inequality. So we're interested in the case where delta is between 0 and 1. And again, the weak Poincaré inequality holds, and alpha of r is given by this function. Just briefly comment that although these are two specific examples, because the weak Poincaré inequality is stable under bounded perturbations, which is if we take a bounded smooth perturbation of u, then we recover the same weak Poincaré inequality up to a constant. What this is saying is that this describes the behavior for any measure where the tails are of polynomial type, provided sufficient smoothness, or sub-exponential type. So that was the weak Poincaré inequality, which is this tool that we're using to get from the geometric to the subgeometric setting. So where are we? Well, we said that we've got the derivative of h as these three types of terms. The microscopic term just followed from the structure of the PDMP and the fact that we had refreshments. The macroscopic coercivity, well, now we know what this operator t pi star t pi is. You may ask about this function phi, but I'm going to gloss over this for this talk and just say that this doesn't cause any problems. And we can use the weak Poincaré inequality to control this term. So now we have these three terms left. Well, it turns out the final term also doesn't give us any major problems, and this is just generally a bounded operator. You can roughly guess that this should be the case, because TA, if we just sort of ignore all the pi's and adjoints, roughly looks like t squared over 1 plus t squared. So we can guess that this, in theory, should be bounded. And of course, one has to prove that. But the other two terms are the ones I want to discuss. So these terms we can write in terms of this function uf. So I've written it out for the AS term, but there's a similar expression for the AT term. So we can bound these two terms in terms of the derivative of uf, the inner product of the derivative of uf and the derivative of u, and we will also need the second derivative of u. What is uf? Well, uf is the solution to this Poisson equation, which is 1 plus nabla star nabla, where nabla star means the adjoint in L2 pi, and is equal to pi of f. And this arises because the left-hand side of this, 1 plus nabla star nabla, is the same as 1 plus t pi star t pi, which is arising in A. So again, sort of roughly looking at it, t involves a derivative, and then 1 plus t pi star t pi inverse involves solving the Poisson equation. So you can imagine that this is going to give terms that look like derivatives of the solution to the Poisson equation. So we need to understand the regularity of the Poisson equation. There's another ingredient into this calculation. So if uf is the solution to the Poisson equation, it turns out that we can bound the function, its derivative, and its second order derivative in L2. And the result that we need to do this was shown by Lorenzi and Lunardi. Remark here that one of the difficulties of this is that we always have to worry about whether or not these functions are in L2 anyway, due to the low decay rate or the slowness of our heavy-tailed distributions. So in the geometric setting, we knew that we had exponentially decaying tails of our measure. So if we had polynomially bounded solutions to the Poisson equation and its derivatives, we would know that these terms make sense. But we need to be a bit more careful in the subgeometric setting, which is why the paper by Lorenzi and Lunardi was useful to us, because they work by applying cutoff functions. So they only ever work in a bounded domain, and then in the last moment take the limit to the full domain once they've got the required estimates. So with these main ingredients in place, the abstract theory of hypocoercivity, the weak Poincaré inequality, the derivative estimates to control the remainder, we're now in a position to quote what our main theorem was, which is that the semigroup converges with a rate given by psi. And what is psi? Psi is the inverse of alpha squared times log of r. And we've also had to pay this price, this oscillation term. So in principle, we've now described what is the rate of convergence. But of course, it'd be nice to understand what actually is psi. So let's just go back to these two main examples that we considered earlier. The one of the polynomially decaying tails. So when u was given by its log of 1 plus mod x. Then we said that alpha of r was of order r to the minus tau. And we find that psi is t to the minus 1 over 2 tau. And for example, so the subgeometric example, alpha of r is given by this expression, and then psi is given by an exponential of minus kt to this power, delta over 8 minus 7 delta. So we've seen that in the polynomial decaying example, we have a polynomially decaying rate, and in the sub-exponential example, we have a sub-exponential rate. So I'm just going to finish by giving the references. And thank you all for your attention.